Okay, this is the introduction to the capacitive reactance lab activity. The lab objectives are to calculate capacitive reactance, and we calculate capacitive reactance two different ways. To observe the relationship between frequency and capacitive reactance, and to observe the relationship between capacitance and capacitive reactance. What's required for the components for this lab are two 0.01 microfarad capacitors and a 1 kilo ohm resistor. The lab concentrates on two formulas for calculating capacitive reactance. One formula for calculating capacitive reactance is capacitive reactance equals 1 over 2 pi Fc, where F is frequency, C is capacitance. The other formula is a formula very similar to Ohm's law. Capacitive reactance equals voltage across the capacitor divided by current flowing to and from the capacitor. See, that's very similar to what you learned in Ohm's law. For DC circuit, resistance is voltage divided by current. Our opposition in the circuit is capacitive reactance. Okay, the first thing you're going to do is you're going to fill out table or chart 1. Chart 1, you're just taking a look at what happens if you have a 0.01 microfarad capacitor in the circuit, and you keep changing the frequency from 10 kilohertz up to 100 kilohertz. The formula that you will be using is capacitive reactance equals 1 over 2 pi times the frequency times the capacitance. So for 10 kilohertz, you just plug in the values. 2 pi, put in your 10 kilohertz, put in your capacitance value of 0.01 microfarads, and calculate the capacitive reactance if you have a 0.01 microfarad capacitor and you apply 10 kilohertz to that capacitor, and put that in this chart. Then you're going to repeat that calculation until you get to 100 kilohertz. You should see the numbers decreased because as you increase the frequency, capacitive reactance decreases. Next, we're going to apply the formula that capacitive reactance can be calculated by taking voltage across the capacitor divided by current flowing to and from the capacitor. And we're going to set up a little series circuit to prove this out. Now, you notice there's two figures on the lab activity. There's figure 1 and figure 2. You have figure 1 and figure 2 because if you have a scope that's connected to ground, you can have some ground loop problems. So you need to switch the components around. You're using a Fluke 123, which does not provide any ground problems. So we can just use figure 1. So you're going to set up the circuit. You're going to take and breadboard up a 0.01 microfarad capacitor in series with a 1 kilo ohm resistor. Then you're going to connect the generator to that circuit, set it for a sine wave, set it so that you have 5 volts RMS coming out at a frequency of 10 kilohertz. On this experiment, as you change frequencies, make sure you keep it at 5 volts RMS coming in. Next, we're going to gather information to fill out the table below. First thing we want to know is voltage across the resistor. So all you have to do is take channel 1 and place it directly across the resistor. Measure that voltage. Typical voltage you might measure maybe 2.72 volts. Now why we need that measurement is to find current. Because we can find current flowing through the resistor by taking voltage across the resistor divided by the resistance. Well, if you take 2.72 volts divided by 1 kilo ohm, you end up with 2.72 milliamps. And since it's a series circuit, that's a current flowing at all points in the circuit. So that's the current flowing to and from the capacitor. Now you might say, well, why don't we just put an ammeter in the circuit to measure current? Well, a digital ammeter cannot measure current at high frequencies. So we have to go to this approach of measuring the voltage across the resistor and calculating the current flowing through the resistor to determine the current in the circuit. Next, we need to know the voltage across the capacitor. So what you're going to do is you're going to take and remove the scope from across the resistor and just place channel 1 directly across the capacitor. So put channel 1 here, put the ground lead on the scope here, and measure the voltage across the capacitor. Now I measured something like 4.07 volts. Now we're ready to calculate capacitive reactance, because capacitive reactance equals the voltage across the capacitor divided by the current to and from the capacitor. We have the voltage across the capacitor, it's 4.07. We have the current, 2.72 milliamps. I believe that calculates out to a capacitive reactance of 1,492 ohms. So that's the opposition to current flow offered by that capacitor at a frequency of 10 kilohertz. Now that should compare favorably to what you've calculated up here. It will not be exact, but it should be somewhat close, and the numbers, as you calculate them, should go in the same direction. Next, you're going to graph out the relationship between capacitive reactance and frequency. So you should see that as the frequency increases, the capacitive reactance decreases. Next, you're going to see what happens when you increase the capacitance in the circuit. So we're going to do the same experiment again. We're just going to increase the capacitance to 0.02 microfarads. Now we have 2.01 microfarad capacitors. So if you put the 2.01 microfarad capacitors in parallel, you'll end up with a capacitance total of 0.02. So that's how you obtain 0.02 microfarads of capacitance to complete this lab. So chart 3 again is calculations, just using x of c equals 1 over 2 pi fc, and chart 4 is using the voltage measurements in order to figure out what the capacitive reactance is. Okay, when you complete this, you have a few questions dealing with capacitors and capacitive reactance that you can find in the textbook. Also, at the end of the lab, there's some questions right directly out of the back of the textbook. And that concludes the introduction to the capacitive reactance lab.